Welcome to Math 1314. This is section 1.7. We are looking at equations that have inequalities. So mathematically, we have four different symbols to represent an inequality. Two of them have no lines under the bottom and two do. The lines mean it is also possibly to be equal. So let's see. 2 greater than itself is not true, but 2 greater than or equal to itself is true. So this one with the line includes the possibility of equality. Now we all agree that 2 is less than 3. And notice we're pointing at the smaller number. Now, what happens if we add, subtract, multiply, or divide both sides by something? Does this inequality remain true? Let's see, 2 plus 1, 3 plus 1. Well, that's a 3 and a 4. 3 is still less than 4. If I subtract 1, 2 minus 1 is 1. 3 minus 1 is 2. 1 is still less than 2. 2 times 5 is 10. 3 times 5 is 15. 10 is less than 15. And if I do division, it's still true. So what that means is I can solve these problems like normal equations, adding, subtracting, multiplying, dividing, and the inequality will remain true. But there is one exception, and that exception is the following. If I multiply both sides by a negative number, so this is our big exception here. 2 times minus 3 is minus 6. 3 times minus 3 is minus 9. Is it true that minus 6 is smaller than minus 9? No, if I'm thinking about a number line, minus 9 is certainly to the left of minus 6. Now, it would be true if I flip the inequality to point the other way. So that's going to be the secret. If we multiply or divide by a negative, the inequality points the other direction. I can add and subtract negatives and there will be no change. It's only, and again, only if you multiply or divide by a negative number. We need to look at something called interval notation, and in terms of open dots and closed dots. Supposing I'd like to graph all of the numbers x that live in between 1 and 3, with the possibility that I could equal to 1. Well, 1 and 3 are involved. Because of the equals, this is a closed-in dot. It's all the numbers trapped in the middle, so all of this is shaded. 3 is not included, and so that's a open dot. And so this is a graphical representation of all those numbers. In interval notation, we write the smaller number on the left, comma, the larger number. Closed dots get brackets. Open dots get parentheses. And again, open dots from this inequality, and the ones with equals get a closed dot. What if I wanted to graph all the numbers bigger than 2? Alright, so here's 2. It's an open dot because 2 is not included, and it's everything bigger. So how do I represent that? Well, that's 2 comma infinity. Infinity represents going to the right forever. Open dot gets a parenthesis. Infinities, positive or negative, get parentheses. What about all the numbers less than or equal to 4? All right, so here's 4. It's a closed-in dot. Goes off to the left forever. Left forever is minus infinity up to 4. 4 is a closed dot, so a bracket. Infinity, again, always gets a parenthesis. What if I wanted all the numbers here to the left of minus 2, or I wanted all of this stuff off to the right bigger than 2? Well, let's see. Here's all the stuff from the left, minus infinity to minus 2 with a bracket because of the closed dot. The right-hand piece would be bracket 2 to infinity. And since I want both of them, we glue them together with this U for union. You'll also see this symbol associated with the word or. Alright, so with all that aside, let's look at solving some problems. So here in question 1, we have an inequality. I'd like to solve it like a normal equation. Remember, the only exception is if I multiply or divide by a negative number. So let's see, I'm going to subtract 3. Alright, so 31 minus 3 is 28. Alright, I would like to divide. I want to get rid of this minus 4. But as soon as I divide both sides by the minus 4, the inequality now points the other way. And I get all the numbers less than minus 7. Alright, so graphically, it's an open dot at minus 7, goes off to the left forever. Interval notation, minus infinity to minus 7. Infinities get parentheses, open dots, parentheses. And the last is what's called the set builder notation. And it's just a fancy way of saying all the numbers m and the vertical line is such that they are less than minus 7. So that's why they ask you here for this thing called set builder notation. There was our interval notation. And graphically, when you graph it in Connect Math, it's going to be an open dot, but I believe when you graph it, it's going to look like a parenthesis there at minus 7. All right, question 2. Alright, the only added complexity here is I've got this group of parentheses. So I'm going to distribute in the 6. So 6 times W, 6W, got a minus 24 plus 3. Minus 24 plus 3 is a minus 21. And so now what? Well, I'm going to bring this minus 21 over with its friend on the left. So 21 minus 9 is 12. Alright, and so I divide both sides by 6. No problem. Doesn't flip anything, and we're done with that. Now, you can leave it like that, but the problem is I've heard some students tell me before, oh, okay, here's 2. Yes, it's an open dot, and since this is pointing to the right, you're going to shade to the right. Well, if you have a doubt which way to shade, pick a test number. Supposing you picked 3. Is it true that 2 is greater than 3? No. But if you pick 1, is 2 bigger than 1? Yes. And so you'll see it is the stuff to the left. You can also just flip it around and write it in a different order. That's okay. 2 is pointing at the W. 2 is still pointing at the W. And so there's our picture. Set builder notation is all the W's such that W is less than 2. Okay, so set builder, interval notation, and then graph it. All right, question 3. We have all of these terrible fractions. I'd like to get rid of the 12, the 6, and the 36. So I need something to multiply by that all of them would go into. Well, 36 goes into all of them. So I'm going to multiply each and every piece by 36. 12 goes in there 3 times, so I've got 3 times 1 plus y. 6 goes in there 6 times, so 6 times this piece, and don't forget the minus. These 36's cancel, and I get a minus 1. So now we distribute 3 times 1, 3 times y, minus 6 times y, minus 6 times 3. All right, anything I can collect together? Well, yes, 3y minus 6y is a minus 3y. I've got this 3 and that minus 18, so a minus 15. And now bring it to the right. And so I've got minus 1 plus 15, which is 14. We're almost there. Hang in there. So now I need to divide by this negative 3 to clear it. But as soon as I do that, I know the inequality will flip around to look the other direction. Okay, so that gives me y is less than a minus 14 thirds. All right, so that's coming this way. And I need to know about how big it is, so when I go to graph this, and it's about minus 4.666. So let's see our set builder notation. Got that. Interval notation, it did go off to the left forever. And so now when you graph it, well, you might say, well, how do I graph a minus 14 thirds? There's no mark for that. Well, remember we saw that minus 14 thirds is about minus 4.66. So just make your mark a little past halfway, and close is good enough for Connect Math. All right, in question 4, we're going to look at the difference between the words and or. And represents intersection, or what is the common part. And that looks like this symbol that's upside down U. Or is a union where we lump everything together. So in both of these cases, we're graphing the same sets. The only difference is the word connecting them. So let's see, all the stuff less than minus 2 and all the stuff minus 6 and bigger. All right, so in using the word and, we are looking for what's in common between these two. Well, let's see. Minus 6 is in common, everything up to, but not including minus 2. And so that's how it would look in our interval notation. All right. And then they asked you to graph that, and we can do that. In the third part, we are looking at the or the union, and we're going to dump everything together. So let's go back and look. what if we dumped everything together? All of this stuff. So if I dump it all on one number line, I'm certainly going to get everything under minus 2. If I now dump in all of this stuff, all right, so I'm going to dump that stuff in. Okay, so I'm dumping it in all together. So this one has a minus 2, and so I'm going to dump it in, fill that together. And so when I look at this and I want to figure out what's there, let's see, is that there or not? And the answer is yes, it is in there, because one of them had it, the other didn't. We dump it all together. So it's not excluded. And so what we get is the whole number line is shaded, and even this little dot. And again, it's shaded because this piece had it, which would fill it in. Okay, so be careful with what's in common and what is not. All right, in question 5. In question 5, we have a double inequality. Our strategy is to isolate the variable in the middle, and we want to work on all 3 parts at one time. Let's see, minus 1, minus 1, minus 1. Okay, minus 1 is a minus 2. These cancel. I get a minus 5x. 0 minus 1 is negative 1. So finally, to get the x alone in the middle, I need to divide by a negative 5. But wait, if I divide or multiply by a negative, all inequalities must reverse. So here's me dividing by minus 5. This inequality turns around, so does that one. A negative over a negative is a positive, and so we've got 2/5 greater than or equal to x greater than 1/5. We can turn it around. Just make sure everything is pointing the way it was before. 2/5 is still pointing at x. X is still pointing at 1/5. And so this would be 1/5 open dot, 2/5 closed dot. And so here is our interval notation. Now how do you graph that? Well, that's not so easy. They give us this giant number line. 1/5 is in terms of a decimal 0.2, so pretty close to 0. 2/5 is 4/10 or 0.4, so it's not even quite halfway. But again, as long as you're reasonably close, Connect Math will accept it. All right, let's see. So again here, I want to get the variable alone in the middle. It's got this ugly fraction under it, so I'm going to multiply through by 5 to get rid of it. So here's the 5 times all pieces. 5 times minus 2 is a minus 10. These 5's cancel. 5 times 5 is 25. All right, so far so good. I want to get rid of the minus 3, so I'm going to add 3 to both sides, all sides. 10 minus 3 is a minus 7. This one goes away. 25 and 3 is 28. And so finally, I'm going to divide everything by 5. And we get minus 7/5 less than or equal to x less than 28 over 5. So because of the inequality, I get a bracket on the left and a parenthesis on the right. Now, I don't know about you, but I don't have any feeling about how big those numbers are. So I made them into decimals, so when I go to graph it, I can get reasonably close. Let's see, I need a negative 1.4. All right, that's not quite halfway. And I need a 5.6 for this side. And that's a little more than halfway. So not too bad. Next, we change our focus to looking at absolute value. Absolute value looks like two vertical lines. Absolute value of 5 is 5. Absolute value of 0 is 0. And the absolute value of minus 3 is, now typically we think of this as absolute value of minus 3 is 3. Well, the way it does that is it takes the inside part and it multiplies it by a negative 1. So negative 1 times negative 3 is a positive 3. That's why if you look at the definition for absolute value, you see absolute value of x is x anytime the number is 0 or bigger. And if it's negative, then the way you get rid of the negative is to multiply it by a negative 1. Now, an important thing to see here is the absolute value of a number is always 0 or positive. It is never negative. That's not possible. Absolute value always gives you 0 or positive. So, let's say I wanted to solve absolute value of x is 4. Well, there are two numbers that would work, plus 4, minus 4. Because absolute value of 4 is 4, and absolute value of minus 4 is also 4. What about absolute value of x is minus 2? Well, there's no solution. That's not possible because absolute value is never negative. What about if I had x plus 1 on the inside? And in absolute value, I want that to be 10. Well, if the inside calculates to 10 or minus 10, it'll still work. And that's why when we solve this, it's x plus 1 equals plus or minus 10. Alright, so if I use the plus, minus 1 plus 10 is 9, and you can check that that does work. And minus 1 minus 10 is minus 11. And minus 11 plus 1 is minus 10. But in absolute value, that's still just 10. Alright, what if we have an inequality where it is looking back toward the absolute value? Notice the pointy part is looking at this guy. And in this next example, it's looking away. Now that's really, really, really important because how we solve these two problems is different, all depending upon the direction of the inequality. In this case, we turn this into the kind where it's trapped in the middle between the number and its negative. So then I solve it like I did before, subtract 1 from all parts, and I get everything between minus 11 and 9. Close dots, so brackets. If it's looking away, instead of a trapped problem, I get two separate problems. One is x plus 1 greater than or equal to 10. So x is greater than or equal to 9, which is all this stuff. In the second problem, so the first is exactly like it's written, but no absolute value. Second one, same inside, but there are two changes. Inequality is around the other way and the negative of the number. And so I get x less than or equal to minus 11, which is all this stuff. Since I've got two pieces, I need this u for union, so I get my answer in interval notation. So these are some examples. All three of these, 3, 4, and 5, are all basically the same. How we solve it changes whether it's equal, looking toward, or looking away. All right, so in question 7, they're going to give us three problems that almost look identical. The difference is equal, looking toward, and looking away. Equal. All right, clean it up, move the 3, and so I get y plus 6 in absolute value is 6. Easy enough. Inside part could be plus or minus 6. So that's minus 6 plus or minus 6, and I get answers of 0 and minus 12. In the second one, let's see, let me clean it up again. Move the 3, and so I get it this way, and it's looking back toward. So it turns into the trapped kind. Trapped in between the number and its negative. Subtract 6 from everything, and I get everything between minus 12 and 0. In the last case, same deal, clean it up first, move the minus 3. Now, it's looking away. And when it looks away, we've got two problems. First is exactly like it's written, 6 minus 6 is 0. Second one, inequality looks the other way, and I've got the negative of the number. So everything less than or equal to minus 12. And so what you can notice is when it was toward, it was stuck in the middle. When it looks away, your answer is away. And when it's equal, it's just the two dots. And in this last case, because I've got two pieces, I've got this U for union. All right, question 8. Let's see. Clean it up. So first, move the 2. So 22 and 2 is 24. Divide through by 3. Easy enough. 24 divided by 3 is 8. Okay, so let's see. It's not an equals. It is looking back toward, so it's the trapped kind. I want to isolate the variable in the middle, so I subtract 5 everywhere. So far, so good. And then I see I'm still left with a negative t. I need to get rid of the negative, so I'm dividing everything by a negative 1 or multiplying by negative 1. In either case, the inequalities flip. All right, and so I divide this by minus 1, this by minus 1. This one should be by minus 1, too. Not sure why I didn't in the notes. And so that would be 3 over minus 1, giving me a minus 3. That would be a minus 3. So again, dividing everything by a minus 1. And let me fix that up as well. Okay, let's see. And in our last problem, kind of a strange problem, we've got the absolute value of y less than minus 7. But the absolute value of any number is always 0 or positive. So how could I have 0 smaller than minus 7? Or even a positive number smaller than minus 7? That can't happen. So therefore, there's no solution. There's no number you could ever put in there to make this a true statement. Let's see, absolute value of y equals minus 7. Well, that's no solution again for the same reason. Because this absolute value, doesn't matter what number you stick in there, is always 0 or positive. And finally, the last strange problem, absolute value of y greater than minus 7. I don't know, let's just pick a few numbers and take a look. Absolute value of 3 is 3. Is 3 bigger than minus 7? Yes. You say, well, where did the 3 come from? Well, I just picked a random number. I could have picked 5 or 10 or 5,000. I just picked 3. What if I pick 0? What happens if I pick 0? Absolute value of 0 is 0. Is 0 bigger than minus 7? Yes. What if I picked minus 100? Absolute value of minus 100 is a positive 100. And is that bigger than minus 7? Yes. So you see, I've picked a positive number, 0, and a negative. Everything worked. So therefore, all real numbers work, and the solution is minus infinity to infinity. So kind of a long section. Take your time and good luck.